but we'll go ahead and get started. So tomorrow, if you didn't print one of these out, it starts off with a quick review. Hopefully last semester you remember that we talked about the octet rule. Basically, that means 8, except for hydrogen and anything that's trying to get that 2 from that first ring. So if you recall, the first ring is 1s, which has 2, and then basically you have all of these other rings. Now here's the trick. We have these Ds that nobody talks about in there. These valence electrons are going to be from the S and P only. S can hold 2, if you recall, and P can hold 6, and that's how we get to that 8. We don't care about the Ds because remember, each one starts with 4s and then 3d, or 5s and then, actually this would just be 2 right here. Let me sneak one more in here. And then another one. Perfect. Beautiful. But once we get up there, we don't care about the Ds. They're not part of the valence electrons. That's why we said anything in the periodic table, anything that was in this area right here, that was D, it had 2 valence electrons because of the S, right? So that's going to be important for us. If you remember, ions, if they gain electrons, they become negative, and those are anions. And if they lose electrons, they become positive, and they are cations. That's the big thing. Ionic bonding is when electrons go from one thing to another, and then that becomes negatively charged, this becomes positively charged, and there is this electrostatic attraction. Again, you can talk during, if you have a question at any time, just make sure that if it's in the chat, I'm not going to see it. Big thing here. The cations become positive, the anions become negative. Can anybody tell me what type of elements tend to make positive ions? Think about our 3 types of elements. Metals, semi-metals, or non-metals? Anybody?
Metals.
Metals, good. Going for Student of the Month this month. Nice. And the negatives are going to be who? Anybody? Who's going to form?
Non-metals.
Non-metals, right? That's why an ionic compound is a metal with a non-metal. The metal is positive, the non-metal is negative. It's easy enough. If we take something, for example, like lithium, we have lithium has 3 protons and 3 electrons. There's our first 2. There's our last one. The number of valence electrons here equals 1. If we take fluorine, it has 9 protons. 2 plus 7 equals 9. This has 7 valence electrons. This 1 electron here will bounce to here, making this have a negative 1 charge, an 8, and then this will have just that 2, and it will have a positive 1 because it lost 1. That positive charge from the, lithium, not sodium yet, and the fluorine will cause that lithium fluoride. The fact that this loses 1 and this gains 1 makes it a 1-to-1. If this gained 2, then we would need 2 to be lost. So it would be something like for example, if this were oxygen, this would need 2, so we would need Li2O. That would be the lithium oxide. That's ionic bonding. Molecular bonding is a little bit different. If we take a look, let's take oxygen. We have 8. Here we have 2. And then we have 6. So it needs 2. Let's look at it differently. Instead of looking at it losing or gaining, let's look at its box diagram. The 1s is full. The 2s is full. That means 4 of these electrons, right? 6 minus 2. It's 1s2, 2s2, 2p, 4. Right? 2 plus 4 is these 6 valence electrons. Different ways to get it. Also, if we look, it is in group 6a. Right? So many ways we could do this. We have 4 here. 1, 2, 3, 4. It's missing 2. If it could gain 2 from something, like take them away because it's electronegativity being high, that would be great for this oxygen. It would fulfill the octet rule. If it cannot pull those electrons away, for example, hydrogen has 1s1. Here's the 1s, it only has 1. If this were able to share this electron with it, then what we would end up with, and let's just let's write this going down because we make the spin up, right? If one's that's going to fit the way we need it to be. If we have 2 of these, we can fit those in there. And what you're going to end up with is H. I'm just going to make this right here. Here's the O. And here's the other hydrogen. Now we know that oxygen has 1, 2 from the S2, right? And then it has these 2 right here, which are also paired up. We call these lone pairs. Those are those 2. Now these 2 boxes here are represented by these boxes. 1 from each of the oxygens and 1 from each of these hydrogens. That creates a shared pair of electrons. A shared pair of electrons is also called a covalent bond. Now, why wasn't able to pull these away from them? Because remember, some things have a low ionization energy and some things have a high electronegativity. It just so happens that these electronegativities for these guys are enough that it's not and the ionization energy for this is high enough that it's not able to just pull it away from it. This is called a shared pair. And we'll find out later that this is not an equal sharing. This is like the uncle handshake. Those of you guys that have had the uncle handshake where the uncle's like tries to overpower you or whatever, that's what's happening here. The one with the higher electronegativity is actually going to be the one pulling the electrons a little bit closer. But the fact that it doesn't pull those electrons away makes that a covalent bond. Now, who does this happen with? Well, this happens with our semimetals and our nonmetals. The metals have too the metals have too low of an ionization energy that their electrons will be pulled off. These guys, it becomes a tug of war. And that's when we get into the molecular bonding. Now, the fact is that these can pair up in many different ways, and that's why we have to use the prefix rules for these. Molecular bonding or covalent bonding, we need to name these with prefixes. If you recall, this would be called dihydrogen monoxide. All right? Now, the way you figure out how to draw this is kind of interesting. The first thing you do is you count the valence electrons. Now,
is this packet on Canvas?
It is. It is.
Where?
And you'll get it tomorrow as well. It's actually in the assignment.
Okay.
Yep.
Thank you.
You'll get a copy tomorrow. All you need right now is basically just a blank piece of paper. I'm just kind of using this. But if we take a look, if we have the electron configuration, we look for the highest number and we count the electrons. 2 plus 3 equals what? Hopefully you said 5, right? And if we look, there's another way we can see this as well. By looking at a periodic table, it's in group 5A. So it has 5 valence electrons. If we look at hydrogen, what group is hydrogen in? Yeah, and if you're going to answer a lot of questions, you just keep yourself unmuted. Louder?
1A.
1A. So we have a P. The formula is pH3. We know that 5 valence electrons is what phosphorus can bring to this party. Hydrogen can bring 1, but how many are there?
3.
3, right? Yeah. Remember, the first day is the easiest, so if you want to unmute and answer all these, that's good. 5 plus 3 equals what?
8.
8. There we go. We have 8 electrons to do all the bonding here. 8 valence electrons. So here's the next part. We have to figure out who goes in the middle. Well, there's only one choice here. That is P. Do you guys know the term uniqueness? If there's one of something, it's going in the middle. P will go in the middle. We will bond that P with H's. They will share electrons because, again, this is pH3. Both of these are not metals, so this is how they would bond. These electrons right here are shared. If we look at this diagram, how many electrons are shared in a bond? It's a pair, which means that there are 2. We said we had 8 electrons to play with. So 2, 4, and 6 are already taken care of. 8 minus 6 leaves us with 2. Only one of these needs an octet. Hydrogen fulfills the octet with 2, so it only gets 1 bond. It is done. Remember, that was that first ring we talked about. Phosphorus is not in that first energy level. It will have an octet. It already has 2. It already has 3 bonds with 2 each. That's already 6. It now needs 2 more. So if they're not bonding pairs, then they are lone pairs. Phosphorus will get that lone pair. We would say that this has 3 bonds and 1 lone pair. We could try that with NH3. It's the same game. We have 5 and we have 3. So N will go in the middle. H, H, H. 1 lone pair. All it's asking you to do here is add up the numbers. 5 plus 3 is 8. How about SO2? Well, find S. 6. O. 6. 6 plus 6 times 2 is 18.
12 with 2.
Plus the 6. You're right. Yep. 18. 2 times 4. And then 2 times 2. 2 times 4 is 8. 2 times 4 is 8, and 4 times 1, 1 times 4 for the hydrogen is 4. So that's a total of 12. That's this whole game right here. That's the first step, is figuring out the number of valence electrons total. When you're writing something, a bond can be written as a line. Lone pairs can be written as dots or lines. If we have HF, that is 7 and 1 for a total of 8. Is there a true center here? No. So we know that they're going to connect each other like that. The hydrogen only gets the bond because all it's worried about is that 1s2. The fluorine needs that 2s2 and that 2p6 to be full. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And then that extra one from hydrogen gives it that octet. Now these are being shared, so they can actually be considered for both of them. 2 for the hydrogen, and these 2 plus these 6 for the fluorine. So the one that fluorine brought to the party and the one that it's now sharing with the hydrogen, that equals the 8 that we need for that octet. If we take a look here, this gets a little crazier. Nitrogen and iodine. There's only one nitrogen, so it's going to go in the center. It brings 5. Each iodine brings 3. Each iodine brings 7. 3 times 7 is 21. That's a total of 26. Don't let this fool you. We've been dealing with hydrogens, so we hadn't had to worry about everything else getting the octet. Currently, we have 2 plus 2 plus 2. That's 6. So 26 minus 6 equals 20 left over. Each one of these has to fulfill the octet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 20. Right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Count them up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That's all of these electrons. Each of these iodines brought 7, one of which was here, and each of the nitrogens brought 5. The one nitrogen brought 5, one of which is here. The fact that they're sharing this, that's the covalent bond, right? These are the 6 it brought, yes, but the one extra is the 7th there. The nitrogen brought 1, 2, 3, 4, 5. They're sharing these. That's the covalent bond. We would say this has 1, 2, 3 bonds and 1 lone pair. 3 bonds and 1 lone pair. Take that piece of scrap paper you have and try to draw this one out. CCl4. I'll give you 2 seconds for that. All right, so we have 7 times 4, which is 28, and 4. That's a total of 32. Carbon is the only thing that's by itself. And I'm going to jump. The skeleton structure for this would just be this. It's a very simple structure. And then we're going to put the lone pairs on everything. Well, remember, carbon brought 1, 2, 3, 4 to the party. Each of these chlorines brought 7. 1, 2, 3, 4, and then 6 for each one, right? So 1 and 6. 1 and 6. 1 and 6. 1 and 6. The bonds are the ones that shared. A lot of time we just talk about the central atom, and it has 4 bonds and 0 lone pairs on it. Each of the other ones has 1 bond and 3 lone pairs, but when we're talking about a shape, which we're going to get to later, all we care about is the central atom. For the Friday assignment, to kind of get the points for this, try this one out and submit that picture. And then there's one last page, and it is on page 13. Try these out. It's just number 1 on this last page. And then we'll get the rest tomorrow, guys. Questions? Interesting way to start the semester. We'll catch up tomorrow. That's what I got for you guys. I think this ends in 1 minute, so thank you very much.